Increased knowledge of the seafloor allowed scientists to develop the theory of plate tectonics. So, what do we actually know about this mysterious domain beneath the waves? Well, this lecture is a review of important seafloor features and their origins. This raised relief map shows the topography of the seafloor as we know it, and most of these features were unknown before the middle of the 20th century, before the Second World War. Earth's oceans cover about 71% of its surface area. The oceans include more than 97% of all water. That includes water ice, liquid water, and water vapor. The oceans consist of mostly deep ocean basins, with depths averaging more than 3,700 meters. That's more than 12,000 feet, and are underlain by mafic oceanic crust. More shallow areas of the continental margins have depths averaging less than 130 meters. That's about 400 feet. Since World War II, the seafloor has been mapped by mainly sonar and satellite radar, with other methods as well, and these have shed light on many of the mysteries of the deep ocean basins. The following is a review of what we know about some of the different areas of the seafloor. Let's start with mid-ocean ridges, which occur at oceanic divergent plate boundaries and include the Mid-Atlantic Ridge, the East Pacific Rise, the Indian Ocean ridges, the Juan de Fuca Ridge, etc. The mid-ocean ridge system spans the Earth like seams on a baseball, with its cumulative length exceeding 70,000 kilometers. Although these features rise several kilometers on average above the surrounding abyssal plains on the seafloor, they have a very low aspect ratio, which means they are very wide compared to their height. Mid-ocean ridges are highly segmented, offset by numerous transform faults. The nature of this segmentation is still somewhat controversial, but is likely to do with the changing local spreading rates and directions, which in turn affects magma generation and ridge formation. There are about 15 major mid-ocean ridge systems, made up of two fundamental types based on their spreading rates. Fast-spreading ridges, or rises, have spreading rates from 9 to 20 centimeters per year. These ridges are broad with smooth overall topography and a small axial trough. The East Pacific Rise is an example of a fast-spreading ridge with spreading rates up to 20 centimeters per year. Slow-spreading ridges have much lower spreading rates, typically less than 4 centimeters per year. These ridges have more rugged topography with large axial rift valleys. The Mid-Atlantic Ridge is an example of a slow-spreading ridge with spreading rates of about 2.5 centimeters per year. Ridges that spread at rates less than 2 centimeters per year are referred to as ultra-slow spreading ridges and include the Gackle Ridge in the Arctic Ocean and the Southwest Indian Ridge in the Atlantic and Indian Oceans. Mid-ocean ridges are composed mostly of mafic rocks, where basaltic pillow lavas form above sheeted dikes and gabbro. The axial troughs, or rift valleys, include abundant hydrothermal vents, many of which are known as black smokers. Exotic ecosystems have been observed that include extremophile organisms that feed off the chemistry and thermal energy of the hydrothermal vents. Located between the mid-ocean ridges and continental margins are the abyssal plains, which form a huge expanse of the seafloor that lies at depths of 4,000 to 6,000 meters. These areas form around 50% of Earth's surface. Abyssal plains can be considered the flattest places on Earth due to their simple geology and burial beneath layers of deep-sea sediment. Water temperatures at these depths hover between 0 to 4 degrees C. The sediment covering much of the seafloor includes a few basic types. Terrigenous sediment is derived from land and includes mud and sand delivered by large river and glacier systems. Deep-sea clay is composed mostly of airborne dust and volcanic ash, with some amount of both calcareous and siliceous sediment. Biogenic sediment is derived from organisms. Siliceous ooze is formed from the deposition of microscopic diatoms, which can eventually lithify into the sedimentary rock chert. Calcareous ooze is formed from the deposition of microscopic calcareous nanoplankton and foraminifera, which can eventually lithify into the sedimentary rock limestone. Deep-sea sediment may seem boring at first glance, but is certainly a different world under the microscope. Hotspots are those areas located directly above an active mantle plume. Decompression melting in the upper part of the mantle plume produces mafic magmas and volcanism that form volcanoes on the seafloor, both as ocean islands and seamounts. Most active volcanism occurs at the hotspot. Away from the hotspot, older peaks erode and subside. If the volcanic mountains were originally islands, then over time they eventually will become seamounts. The Hawaiian Islands and Emperor Seamounts are famous examples of a volcanic chain of islands and seamounts formed over a long-lived hotspot. Many other oceanic hotspots exist all over the world, including Iceland, the Galapagos Islands, Easter Island, etc. Charles Darwin was a famed naturalist and biologist, but did you know he was also a geologist? He was part of the second global voyage of the HMS Beagle, which lasted 5 years from 1831 to 1836. His research during this trip most notably yielded the famous On the Origin of Species, published in 1859. But he also published other important works, including The Structure and Distribution of Coral Reefs in 1842. Coral reefs typically form in the shallow water around volcanic islands. Over time, the coral grows upward as the island slowly subsides, evolving from a fringing reef to barrier reef to atoll. Recent studies have shown that glacial, interglacial sea level changes also play a role in reef development. The Society Islands of the South Central Pacific display the different stages of this process. To summarize, after a volcano breaches sea level, it is subjected to weathering and wave erosion. Coral reefs begin to build up in the shallow water around the shoreline of the island. This is a fringing reef. The island of Moorea, near Tahiti, represents this phase. As volcanic activity ends and the island begins to subside, the land area slowly disappears. The coral reef builds up higher and higher to stay within the shallow waters, forming a barrier reef and lagoon around the diminished volcanic island. Bora Bora is a good example of this phase. With continued subsidence and wave erosion, the volcanic island disappears beneath sea level, and an atoll forms, covered by coral reef, sediment, and a shallow to deep lagoon. Mopiha represents this phase of reef development. Let's explore these South Pacific islands in more detail. The Society Islands of Polynesia are an archipelago of about 14 volcanic islands in the South Pacific. The first Polynesians may have arrived as early as 1,500 years ago, and the island group was later visited by the HMS Endeavour and Captain James Cook in 1769. The Society Islands are made up of the Windward Islands to the east and the Leeward Islands to the west. The exact nature of these islands is still being researched, although a mantle plume origin is most likely, with the current hotspot located just to the east of Tahiti. In general, the volcanic islands increase in age to the west, and are mostly composed of eroded basaltic shield volcanoes, basaltic lava flows and intrusions, and minor andesitic to dacitic lava domes. Additionally, a spectrum of coral reef types are present across the island chain, from fringing reefs to barrier reefs to atolls. These are formed as a function of subsidence of the volcanic peaks, but also from Ice Age-related sea level fluctuations. The Windward Islands include Tahiti and Moorea, with both islands displaying beautiful fringing reefs, locally punctuated by inlets and bays. These islands also show early stages of barrier reef development. Most of Tahiti's population, of around 190,000, live on the lowlands along the coast. With the rugged inland rainforest areas largely uninhabited. Moorea is just a 30 to 45-minute ferry ride to the west. Moorea includes several prominent volcanic ridges and peaks, which rise as high as 3,000 to 4,000 feet and can be seen all the way from Tahiti, where Charles Darwin described the island as a picture in a frame, referring to its mountainous terrain surrounded by coral reefs. 135 kilometers to the northwest is the slightly older Huahine, the easternmost of the Leeward Islands. Huahine has a reef structure similar to that of Tahiti and Moorea. Only about 30 kilometers west, Leighty, as well as neighboring Taha and Bora Bora, all have largely continuous lagoons, separating the barrier reefs from the volcanic islands. Isolated patch reefs can be seen in the lagoon areas, and small elongate islets or motus commonly form along the barrier reef. And Bora Bora is a major international tourist destination known for its luxury resorts. The single break in Bora Bora's barrier reef is Tia Vanui Passage, which provides the only access to the open ocean. The island's central volcanic mountain includes Mount Otimanu and Mount Bahia, which rise almost 2,400 feet above the lagoon. And according to legend, Mount Bahia is where the war god Oro descended on a rainbow. And in the surrounding lagoon, many species of sharks and rays frequent the shallow waters. Farther to the west, Mopiti also possesses an iconic barrier reef. And at about 4.5 million years old, the basaltic rocks of Mopiti's central volcanic island are the oldest in the Society Islands chain. And finally, the three westernmost of the Leeward Islands are all classic atolls, with reefs encircling lagoons lacking any central volcanic island. Mopiha is about 8 kilometers long, and it has a total land area of only 2.6 square kilometers, or about 1 square mile, with only one narrow passage offering access to its central lagoon. About 70 kilometers to the west is the slightly larger atoll Manui. With no navigable passages, its inner lagoon is isolated from the open ocean. However, the atoll is home to large oyster beds and is popular with sea turtles. And 75 kilometers to the north is Motu 1, a 4-kilometer wide, totally enclosed atoll. Seamounts are essentially isolated submarine volcanic peaks. Almost 15,000 of these submerged volcanic mountains are known, of which roughly 10,000 have been mapped. They are typically conical in shape, with heights of at least 1,000 meters, with most being between 1,000 and 4,000 meters in height. Flat-topped seamounts are known as geos, of which 300 have been identified. Along with seamounts in general, geos are very common in the Pacific Ocean. Their origin was somewhat of a mystery at first, but eventually figured out to be a typical volcanic island that subsides over time with wave action planing off much of the top of the volcanic peak, beveling it flat. A shoal or reef complex then develops before the seamount eventually sinks into the deep. In the northern Atlantic Ocean, the Bear Seamount is an example of a geo. The Bear Seamount is one of the New England Seamounts, a chain of submarine mountains that extends southeast from the North American continental margin over 1,000 kilometers across the Somme Abyssal Plain of the North Atlantic. The Seamount chain is crossed by two major submarine currents, the warmer north-flowing Gulf Stream and the colder south-flowing Deep Western Boundary Current. The Nashville Seamount is the easternmost and youngest of the seamounts, which get progressively older to the west. Over 30 volcanic mountains exist along this seamount chain, with the major peaks rising as much as 4,000 meters above the surrounding abyssal plain. Many of the larger seamounts rise to the relatively shallow depths of 1,000 to 2,000 meters below sea level. The more shallow summit depth and the interaction with the submarine currents make several of these seamounts biological deep-sea islands that host hundreds of species of coral, crinoids, sponges, cephalopods, crustaceans, fish, and more. The Mytilus, Retriever, Physalia, and Bear Seamounts lie within the Northeast Canyons and Seamounts Marine National Monument. Located along the upper Continental Rise, the Bear Seamount is the westernmost of the seamounts, and with an age of 100 to 103 million years, it's the oldest one too. This flat-top seamount, or geo, rises up to 3,000 meters above the adjacent seafloor, with its summit roughly 1,100 meters below sea level. Its flanks slope downward at about a 20-degree angle, and the broad summit includes isolated exposures of basaltic bedrock covered by a variably thick layer of sediment that even includes boulders likely dropped by glacial sea ice. Discovered in 1950, Loihi is a notable seamount located only 30 kilometers off the southeast coast of the Big Island of Hawaii. Its summit is a little less than 1,000 meters below the surface, but in time could emerge above sea level, say in 10,000 to 100,000 years. It may have the destiny of becoming the next Hawaiian island. Oceanic trenches are the deepest parts of the oceans. These develop at subduction zones and trend parallel to the volcanic arc. With a depth of just under 36,000 feet, the deepest ocean floor is the Challenger Deep in the Mariana Trench. This is located in the western Pacific Ocean, where the Pacific Oceanic Plate subducts steeply beneath the Philippine Oceanic Plate. This is the Deep Sea Challenger in 2012 at the bottom of its 2.5-hour descent. First visited in 1960, only 13 people have done the dive to the bottom in the following 60 years. The Mariana Trench is the deepest oceanic trench on Earth and is located in the western Pacific Ocean, where the Pacific Plate is steeply subducting beneath the Philippine Oceanic Plate and the Mariana Microplate. In this area, the Pacific Plate is Jurassic in age, between 145 and 200 million years old or so, and is the oldest oceanic crust in the Pacific Ocean. So, the subduction of old, cold, and dense oceanic crust results in increased vertical movement and pull of the downgoing plate and creates progressively steeper subduction angles. This is the process of slab rollback, which may lead to back arc extension and movement of the trench axis as the overriding plate is drawn toward the subducting plate. This type of tectonism may also produce relatively deep oceanic trenches, like the Mariana Trench. The depth of the Mariana Trench varies along its length and is deeper where sediment accumulation is minimal and large Pacific Plate seamounts are absent at the subduction zone. The deepest part of this trench is a narrow submarine valley known as the Challenger Deep. The exact depth has been debated, but the latest multi-beam sonar scans are in general agreement with direct descent measurements, yielding depths between 35,768 feet and 35,856 feet in the slightly deeper eastern pool area. For every 33 feet or 10 meters depth in the ocean, the hydrostatic pressure increases by 1 atmosphere or 1 bar. And all the way at the bottom, pressures exceed 1,000 bars, which is over 1,000 times that of atmospheric pressure at sea level. It's also cold at the bottom, with water temperatures ranging from 1 to 4 degrees C. The floor of the Challenger Deep is layered with fine-grained sediment and very fine-grained diatom-rich siliceous ooze. Sea life is sparse, but includes sea cucumbers, scale worms, and shrimp-like amphipods. Continental margins are those parts of an ocean basin that are adjacent to continents. There are 2 basic types from a plate tectonic perspective. Active margins are located at plate boundaries, like a subduction zone or transform boundary, and include abundant tectonism. The west coasts of both North and South America are examples of active continental margins. Passive margins are not located at plate boundaries and have minimal tectonism. Examples include the east coasts of both North and South America and the west coast of Africa. Continental margins can be subdivided into 3 basic physiographic areas: a continental shelf, slope, and rise. Continental shelf is a very gently sloping, like less than 1/10 of 1 degree, submerged surface that extends from the shoreline towards deeper water. This is an area of shallow water that is typically affected by wave action. The depth of the outer edge of the continental shelf averages around 135 meters, or about 400 feet. This point is known as the shelf slope break. The Bahamas are part of a broad continental shelf area. Submarine canyons may be incised into a continental shelf, representing former river systems that have since been drowned by rising interglacial sea levels. It should be noted that during the periods of glaciation in the ongoing ice age, most continental shelf areas were actually coastal plains above sea level. In our current Holocene interglacial, sea levels have risen several hundred feet during the last 12,000 years or so, inundating the coastal plains and transforming them into the continental shelves we see today. Continental shelf is essentially a sedimentary debris apron deposited on the edge of a continent, and it's composed of both stream-deposited and shallow marine sedimentary material. From seismic studies, we know that it typically overlies the outer part of the continental crust. The continental slope is a more steeply sloping surface, around 4 degrees or so, that extends from the edge of the continental shelf towards the deep ocean. The continental slope continues downward from around 135 meters to around 3,000 meters depth. So most of this area is too deep to be affected by wave action. Submarine canyons are commonly etched into the continental slope, as is seen on the mid-Atlantic continental margin. Steeper sections of the continental slope can actually experience submarine landslide activity, and some of the larger landslides may represent significant tsunami hazards. Again, from seismic studies, we see that the continental slope overlies the area where the continental crust transitions to oceanic crust. The continental rise is a gently sloping surface, like less than 1 degree, that extends out towards the deep ocean abyssal seafloor. This is very deep water, ranging from 3,000 to 4,000 meters depth or so. Material transported down submarine canyons is deposited in this area and can form huge submarine fans. The continental rise generally overlies the oceanic crust and feathers out towards the deep ocean basin. Turbidity currents are dense, muddy underwater currents that are laden with fine-grained sediment. Seafloor turbidity currents are often the result of persistent stream current out onto the continental shelf and down into submarine canyons. They can also be generated along the continental slope by undersea slumping activity. As this submarine density current slows and comes to a rest, the larger material commonly deposits out first, followed by progressively finer-grained sediment. This produces a classic graded bedding sequence. Let's take a closer look at the continental margins of the United States. We'll start with the active margin along the west coast of Central California. The Big Sur area of the Central California coast is part of an active continental margin which typically forms at convergent or transform tectonic plate boundaries. In areas like this, relentless tectonic movement generally results in a rugged landscape having steep cliffs, prominent headlands, and minimal coastal plains and continental shelves. Here we see California State Route 1, which goes by many names, including the Pacific Coast Highway, the Cabrillo Highway, Big Sur Coast Highway, Highway 1, etc. This stretch of the highway hugs the rocky coastline, famous for its scenic views, but also notorious for its destructive landslides. For instance, in 2017, persistent winter rainfall triggered the Mud Creek landslide, which involved about 3 million cubic meters of earth and rock and destroyed over 400 meters of the PCH. The road was reopened about 14 months and $54 million later. Indeed, the PCH has been closed over 55 times in the Big Sur area alone, due to landslides, mudslides, erosion, and fire. Here at Rat Creek, a 2021 debris flow was caused by intense post-wildfire rainfall. In this area, the western flank of the Santa Lucia Mountains is very steep, with sea cliffs bordering the rocky shore and nearshore areas. The coastline lacks large embayments like Monterey Bay to the north or San Luis Obispo Bay to the south, and even small pocket beaches are few and far between. From Big Sur, here is an iconic view to the southeast along the rugged coastline. The continental shelf is very narrow, typically only a few kilometers wide, and is essentially a rocky wave-cut bench formed during previous periods of lower sea levels during the Ice Age. Tectonism is the main factor explaining this coastal topography, where several active faults, including the San Gregorio Hosgri Fault and others, trend roughly parallel to the coastline. Tectonism and uplift are why areas like this are often referred to as emergent coasts. The coastal hills and cliffs are dominantly underlain by highly faulted and deformed Jurassic to Cretaceous units, including metasedimentary and metabasaltic rocks of the Franciscan complex, along with the Mesozoic granitic rocks of the compositionally diverse Selenian block. Tectonically speaking, these rocks are part of the Nacimiento and Selenian blocks, two geologic terrains that comprise most of Central California's coast ranges, and as part of the Pacific Plate, are traveling northwestward along the San Andreas transform boundary from a point of origin farther to the southeast, like several hundred kilometers to the southeast, in the western Mojave area. Farther north is Point Sur and its still operational lighthouse. Point Sur was first mentioned in the logs of Portuguese explorer Juan Cabrillo in 1542. And due to the currents, rocks, and weather, it has long been a hazard to shipping, with more than a dozen notable shipwrecks in the area. Franciscan complex makes up the bedrock at Point Sur, with resistant metabasalt forming the 361-foot-high Sentinel rock outcrop. Connecting Point Sur with the mainland is a marine terrace built on less resistant Franciscan greywacke and covered with a thin veneer of dune and drift sand and marine terrace deposits. An active wave-cut platform extends over 4 kilometers to the south from Point Sur. Marine terraces are originally formed as wave erosion in the intertidal foreshore areas forms wave-cut platforms, which can be uplifted to become marine terraces. Following the PCH and submerged San Gregorio Fault northward, we cross into the granitic Selenian block terrain, eventually coming to Carmel, Pebble Beach, and Monterey. We then cross Monterey Bay and the gigantic Monterey Canyon, one of the largest submarine canyons in the world. Underwater currents and turbidity flows travel through submarine channels, from the coast to depths of almost 12,000 feet at the distal end of its broad deep-sea fan. We meet up again with the PCH as it passes through Santa Cruz on its way north to San Francisco. This area includes actively forming wave-cut platforms along the shore, with textbook examples of Pleistocene marine terraces higher up. These are essentially uplifted former wave-cut platforms. Let's zoom out and get a slightly broader view of this active continental margin. In Southern California, tectonism has created a complex submarine topography of islands, ridges, and sedimentary basins, with no real well-defined continental shelf slope or rise. This continues into central California, where a very narrow shelf yields to a broader fault basin slope area that abruptly descends to the deep sea floor. The shelf widens out a bit to the north and is punctuated by the large Monterey Bay Canyon with its broad submarine fan. Now let's visit the passive margin along the mid-Atlantic east coast. Welcome to the Chincoteague National Wildlife Refuge, along the passive continental margin of eastern North America. If you like wild ponies, historic lighthouses, and long sandy beaches, then this is the place for you. It's located on Assateague Island, part of a long barrier island complex that is separated from the mainland by coastal wetlands that include swamps, salt marshes, lagoons, and bays. The entire Delmarva Peninsula is part of the Atlantic Coastal Plain province. Underlain mostly by soft, sandy quaternary sediment, it forms a relatively flat, low-relief area with the highest point only about 100 feet above sea level. Given its subdued topography, this entire region was subjected to dozens of marine transgressions and regressions that have occurred during the ongoing late Cenozoic Ice Age. During the most recent of the Pleistocene glaciations, sea level was hundreds of feet lower, with the shoreline much farther east near the edge of the continental shelf. The modern continental shelf was then a coastal plain, with Ice Age river systems flowing across it to the sea. With the warmer temperatures of the Holocene interglacial, sea levels rose and the shoreline transgressed landward, submerging the lower ends of several major stream systems, including the Hudson, Delaware, and Susquehanna. Thus, areas like this can be referred to as submergent coasts. Formed by about 3,000 years ago, the Chesapeake Bay is the largest estuary in the United States and has several large tributary estuaries that flow into it, including the Susquehanna, Patuxent, Potomac, Rappahannock, York, and James rivers. The submerged former coastal plain that forms the modern continental shelf is a relatively wide, flat sedimentary platform. Its width varies, but is much wider in comparison to active margin continental shelves. For instance, here in the Virginia Beach area, it is over 100 kilometers wide. Major rivers carved their channels into the shelf and slope, and formed prominent canyons at the shelf-slope break, and into the continental slope and below. This is Norfolk Canyon, originally the distal end of the Susquehanna River system. Indeed, currents still flow through these submarine canyons. Associated with many of these submarine canyon systems are large sediment fans that spread out on the continental slope and rise below. From Virginia to Canada, more than 70 named underwater canyons are present along the edge of the continental shelf. This passive continental margin stretches from Canada down the eastern seaboard around Florida and into the Gulf of Mexico. Well, that's all for now. Till next time.